Your location is not real. It can be rewritten, and you would never know it happened. And it's happening more often than you think. We trust the blue dot completely. When your phone says you're home, you believe it. When your car reroutes you around traffic, you comply. When an aircraft descends through clouds, it follows invisible signals from space. The system feels absolute, objective, mathematical. But that confidence rests on a quiet assumption that the signal coming from space is authentic. It isn't always. The Global Positioning System, GPS, was designed for precision, not for distrust. At its core, GPS is timing. Each satellite carries atomic clocks accurate to billionths of a second. They broadcast time-stamped radio signals toward Earth. Your receiver measures how long those signals take to arrive. Distance equals time multiplied by the speed of light. With signals from at least 4 satellites, your device calculates its position in 3-dimensional space. It's elegant, it's physics, it's geometry. But here's the anomaly. By the time GPS signals reach Earth, they are extraordinarily weak, typically around -130 decibels relative to a milliwatt. That is weaker than background radio noise. GPS receivers work by extracting those faint patterns from noise. They rely on something called the signal-to-noise ratio. The satellite signal is barely above the noise floor. Not loud, not dominant, just detectable. Which means a slightly stronger imitation signal, even by a small margin, can tip the balance. And the receiver will lock onto the stronger one, not because it's smarter, but because it's louder. Your phone can detect them because it knows exactly what pattern to look for. And that creates a vulnerability. If someone nearby transmits a signal that imitates those satellite patterns, even slightly stronger, your receiver cannot easily tell the difference. It will accept the counterfeit signal and calculate a counterfeit position. This is GPS spoofing. Not jamming. Jamming blocks signals. Spoofing replaces them. Imagine you're navigating by listening to 4 distant metronomes. You can't see them. You only hear their rhythm. Now someone stands next to you with a louder speaker, playing a nearly identical rhythm, but shifted slightly. You'll follow the louder rhythm. Your brain has no way to verify the original source. That's what a spoofing transmitter does. It generates counterfeit satellite signals, matches their structure, matches their frequency, matches their timing. Then it slowly shifts. If done carefully, your receiver doesn't jump. It drifts. Your location slides across the map. Meters, then blocks, then miles. A billionth of a second of timing error translates to roughly 1 foot of position error. Nanoseconds become distance, and the device never realizes it has been manipulated. Your navigation system doesn't confirm reality. It trusts signal strength and timing consistency. And both can be engineered. Stop. Think about what that implies. This isn't theoretical. In 2013, researchers at the University of Texas at Austin demonstrated GPS spoofing against a yacht in the Mediterranean. They did not jam the vessel. They did not trigger alarms. They gradually introduced counterfeit signals, slightly stronger than the authentic ones. The yacht's navigation system began adjusting course, subtly, without warning. The crew saw nothing suspicious. The vessel drifted off its intended path. Outside the lab, spoofing has been observed at scale. Commercial aircraft have reported false positioning near high-tension regions. Cargo ships have appeared simultaneously at impossible inland coordinates on digital maps. Entire clusters of vessels have displayed identical false locations. Not random noise, structured manipulation. And the reason it works is simple. Civilian GPS signals were never encrypted. They were designed for openness and accessibility. Infrastructure came first, security came later. Advances in software-defined radio technology have made signal simulation more accessible, raising serious security questions. Now consider what that implies. Aviation, shipping, financial timing networks, power grids, all
Think about
rely
that.
on signals that can be imitated. Stop. Think about that. You might assume modern devices can detect fake signals. Some can, many cannot, because spoofing is not brute force. It is synchronization. A sophisticated spoofer begins by perfectly aligning with authentic satellite signals. It mirrors them, matches their phase, matches their timing. Then it slowly shifts. The receiver sees smooth continuity, no jumps, no glitches. From its perspective, nothing is wrong. To reliably detect spoofing, a system needs redundancy. Multiple antennas to detect signal direction. Cross-checks with inertial sensors. Authenticated satellite signals. Military GPS uses encrypted signals. Civilian systems largely do not, and global infrastructure upgrades move slowly because compatibility matters, because cost matters, because billions of devices already depend on the current standard. We built a planetary navigation system first. We are adding verification later. GPS spoofing reveals something deeper than a cybersecurity flaw. It reveals how modern reality is mediated. Your sense of place, once tied to landmarks and stars, is now algorithmic. When your phone says you're here, you accept it. When your car says turn, you turn. But that here is a calculation based on signals you cannot see and cannot independently verify. The physical world has not changed, but your interface with it has. And that interface can be manipulated. There are two ways to interpret this. Either satellite navigation is a convenience, useful but fallible, or it is critical infrastructure, civilization's nervous system, and must be treated accordingly. Right now, we live in between. The blue dot still moves smoothly. Planes still land. Ships still dock. But the certainty is conditional. Location is no longer a fact. It is a computation. And computations can be rewritten.